Hello, my name is Richard Wheeler. At time of recording, I am currently studying a master's degree in data science at Cardiff Metropolitan University. The following presentation is in regards to the development of a machine learning model to classify walking and driving activities, a study of various data science techniques. Using a mobile phone whilst driving is illegal in the UK, and yet there were 637 casualties, including 18 fatalities, caused by crashes with mobile phone use whilst driving as a contributing factor in 2019. Mobile phone use by pedestrians has also been shown to compromise a user's safety, especially whilst texting. The following study describes the development of two machine learning models for comparison, a machine learning algorithm and a neural network model. These models would be developed to classify a device's activity whilst walking or driving, which could then be used as part of a warning system to notify device users if they are potentially breaking the law or putting themselves at risk of harm. Data collection was performed using MATLAB Mobile to collect mobile phone sensor data. In order to develop a machine learning model, data needs to be collected for training and testing that represents the defined user case. And so it was decided to record the following activities: driving whilst device was in trouser pocket, driving whilst device was in an inside jacket pocket, driving whilst the device was placed on the passenger seat, driving whilst the passenger was holding the device as if it were being used, walking whilst the device was in pocket, walking whilst the device was in an inside jacket pocket, and walking whilst holding the device as if it were being used. Two sets of data were collected, combining all 7 activities. The first would be used as modelling data, and the second for testing the final models. To confirm the potential robustness of the final model, the activities for the new test data were completed using different routes whilst driving and walking than those for the training data. As you can see from the graphs, when selecting the routes taken for both modelling and test, the aim was to make them as varied as possible in relation to both direction of travel and altitude. As you can see, there is a substantial amount of noise in the data. To remove this, code was used that applies a Butterworth low-pass filter. The Butterworth filter is a type of signal processing filter designed to have a frequency response as flat as possible. Using the SciPy L filter function to apply the filter meant that it was passed forward over the data once, which, as you can see from the graph, when plotted against the originals, shows a slight offset between the filtered output and the original. Alternatively, using the SciPy filt method would have applied the filter twice, once forward and then again backward, which would have removed this offset, but this was found to create a large number of null values in the dataset to the point where it became unusable. The final set of data used for modeling and new test data was processed by filtering the individual activities before concatenation into the full dataset. An extra trees classifier model uses randomized decision trees, simple decision rules inferred from the data's features, on subsamples of the dataset and uses averaging to improve the accuracy. As you can see from the code, the tuned model uses different arguments in its setup. They're then used by the algorithm. When comparing against the default settings, which would have been used in the untuned model, you can see the various changes that have been made, including an increase in the number of decision trees used and the maximum depth of each tree. The results from testing both the untuned and tuned model show that both achieved 100% accuracy when tested on the unseen prediction data, but the tuned model performed better on the new test data with an accuracy of 84.84% when classifying the activities. The confusion matrix shows that the tuned model was able to classify all of the driving activities with 100% accuracy, as well as the walking whilst using activity. This makes the model potentially feasible for the defined use case. Tuning of the neural network model was achieved using Keras Tuner, a Python library that makes it possible to iterate over combinations of various neural network architectures. This enabled the tuning of the number of hidden layers, the number of neurons in each layer, the activation function in each layer, number of dropout layers to help prevent overfitting of the model, and the learning rate, which controls how much a model is changed in response to the estimated error when model weights are updated. As you can see from the code, when iterating through the number of neurons, it starts at 32 up to a maximum of 512 neurons, increasing with each iteration by 32. The activation function is iterated through the list. Dropout values start at 0.0 with a maximum of 0.5, iterating in steps of 0.05. The learning rate is also a list of values, 0.01, 0.001, and 0.0001. Additional layers can be added or removed for each tuning session. As you can see from the table, the model architecture with the highest accuracy against the mutator consists of a hidden layer with 448 neurons with a layer activation function of cellular, a dropout layer with a value of 0.4, a second hidden layer with 224 neurons and a layer activation function of ReLU, second dropout layer with a value of 0.05, and a model learning rate of 0.001. This model architecture would be forwarded to the final validation testing. To validate the final model architecture, the model was initially trained using 200 epochs. To improve the model, the epoch accuracy and loss graphs were checked for overfitting, which identified a reduction was required in the number of epochs used during training to 145. As you can see from the code, the batch size parameter was also tuned and was found that a value of 5 was the optimum for this model. As shown, the final model achieved an accuracy of 82.77% against the new test data, but was still unable to predict the walking jacket inside pocket activity, with 84% of the classification of the data related to that activity being misclassified as the driving equivalent. The model can accurately predict the using classes for both the driving and walking activities, which would still make the model feasible for the intended use case. The best model for the intended use case at this stage of development would be the tuned extra trees classifier machine learning algorithm model. Although both models were able to classify the using activities for both walking and driving with 100% accuracy, the neural network struggled to accurately classify the other activities to the same degree as the extra trees classifier model. For example, it was only this model that was able to classify all driving activities with 100% accuracy.